All right, so maybe we can get started. So welcome back, everybody. Thank you for coming again. And I am very excited today to introduce and to welcome Cristina Ramos Almeida. So in the past couple of seminars, we actually saw some of her results that were presented by other people. And now we get to hear from her. So Cristina got her undergrad physics degree at the Universidad de La Laguna, and then went on to get her PhD at the Instituto de Astrofísica de Canarias, or also known as the IAC. After that, she went and did a postdoc in the UK and at the University of Sheffield. And then she came back to the Institute, to the IAC, and she had a Marie Curie fellowship, and then she's been there ever since. One anecdote that I wanted to tell about her is one that I'm not sure she knows. So a few years ago, or quite a few years ago, maybe 6 years ago, I was at a conference, Taurus conference in the UK. And a lot of what people were focusing on was the difference between type 1 and type 2 AGN. So, and, changing look AGN and all these things. So Ski Antonucci, who did some of the first spectropolarimetry of AGN, he was going on and on about how we need to do more polarimetry, blah, blah, blah. And, people were not paying much attention and saying, no, it's too hard. No, the results are too mixed. No, we blah, blah, blah. And then Cristina wasn't there because she was back in the Canary Islands. And then back then, we didn't have Zoom. I don't know if it was Skype. Was it Skype that she came? So without knowing that we had this discussion, she comes and she gives her talk. And her talk, she presents a whole sample of type 2 AGN where she finds hidden broad lines in more than 70% of them. And then everybody was like, oh. So for the rest of the conference, and this is the part I don't know if you know, everybody was talking about the Ramos Almeida results and how we all should be doing more spectropolarimetry. So she totally changed the tone of the meeting. And since then, there's been a lot of papers actually that follow up on this. So anyways, it's my pleasure to welcome you and thank you for coming.
Thank you, Gabi. Thanks a lot for the nice presentation. So yeah, actually, I remember that it was because actually I wasn't in that conference because I just had my first child. I think she was like 1 month old. So I connected from home to give the talk, but I didn't know that people were so interested in the spectropolarimetry, but it's hard, I can tell. I didn't do more. Okay. So thank you so much for inviting me to give this seminar. I think it's a fantastic idea and a great opportunity to talk to you about the work that we have done on different samples of AGN and different volumetric luminosities. So the main points I want to make in this talk is the importance of looking at the multi-scale and multi-phase signatures of AGN feedback in order to understand how it works and how it affects the host galaxies. And this is work, so the first part of the work that I'm gonna present, it's been done with the GATOS collaboration, works led by Santiago García Burillo and Almudena Alonso Herrero. And the second part of the talk on the higher luminosity AGN, it's been done in collaboration with the whole Quasar Fit team, mainly work done by Manuela Bischetti and also Annelise Audibert, who is now my postdoc at the IAC. So let's start. This is an AGN audience, so I don't need to do too much of an introduction, but something that I would like to highlight is that something that has changed in the last years in the way we understand the nuclear activity is that we don't any longer talk about active galaxies, or not so much, no, because I think we understand nuclear activities as a short active phase that can be as short as 0.1 megayears or even shorter than that. in the life of a galaxy. And actually, even more than one AGN episode might take place, depending on whether there is enough gas supply, or that certain conditions are given to trigger this nuclear activity in galaxies. So then this implies that perhaps at least every massive galaxy, containing a supermassive black hole in the center, can go through one or more AGN phases. And then we wonder how relevant is this phase of nuclear activity to galaxy evolution. The popularity of AGN have also increased tremendously in the last few years, I would say. I don't know, 10 years ago, we had our AGN conference and we met together. And now in every conference about galaxy evolution, there is a session about AGN, and you hear the word AGN everywhere. So I think this increase in the popularity, it's mainly due to cosmological simulations of galaxy formation. Not only that, but it's one of the main reasons, I would say, because as far as I'm aware, none of these simulations work if AGN feedback is not implemented. So one of the most known effects of not including the AGN feedback, which is the effect that the AGN produces in the host galaxy, and that can take place in very different manners. It can heat the gas, eject the gas, disturb the gas, and make it more difficult to form stars in galaxies. If they do not include this AGN feedback, the gas cools down, keep on forming stars, and the galaxy grow too big and end up being more like this thing here than this here. So the simulations do not reproduce what we actually observe. So this increase of popularity is something that I'm sure we all appreciate here. So now, I think up to now, we can say that we have plenty of observational evidence of AGN feedback happening on very different scales. So this is one of the main things that I would like to highlight: the importance of looking at multi-phase feedback. Like, for example, if we are talking about winds or outflows, we know that they propagate right from the central engine through the whole ISM of the galaxy, and sometimes we even see signatures of AGN feedback on scales that exceed the boundaries of the galaxy. And we are talking about the CGM, the galaxy halos, etc. So we need to consider these different spatial scales for understanding how feedback works, and also to evaluate how much this feedback is influencing the galaxy. Like I said before, we have plenty of observational evidence of that AGN feedback, or black hole feedback, name it as you want to. It's taking place. So in my talk, I will be focusing on more nuclear AGN feedback, going from torus scales to the central kiloparsec or a few kiloparsec scales. But for example, just an example, a recent paper published in Nature by colleagues at the IAC, Martin Navarro et al., they found that the fraction of quench satellite galaxies in different galaxy halos depend on the position, on the position angle relative to the central galaxy in that particular halo. And this is something that they see in observations and simulations. Somehow the black hole it's having or had any influence on scales as large as the whole dark matter halo. So, starting from the very nuclear region of AGN, back in 2017, Claudio Ricci and myself published this review on nuclear obscuration in AGN. So the idea that we were proposed by the editor was to summarize our understanding of the torus, with the observational evidence that we had from the infrared and the X-rays, and this is what we did. But something that was changing in this period of time when we wrote this article was that we did not any longer understood the torus as a static structure that only does the type 1, type 2 classification. This is one thing, but it's not the only one. But more importantly, we understand now the torus has a dynamic structure that may change with the different AGN periods. So it might appear or disappear, or at least its properties may change. It's a very complex structure in which we see rotation, turbulence, non-circular motions. So nothing to do with the static structure that we all have in our minds, I think. And also it's a structure that serves as the connection between the host galaxy and the supermassive black hole. In fact, the innermost part of the torus is still under the influence of the supermassive black hole in the sphere of influence. And it's, like I said, a structure that, as I will show, based on observational evidence, it's connected with other structures of the galaxy through gas streamers. So, like I said, this is something that we try to capture in this review, and like trying to put together, like I said, the information that we have from the infrared and the X-rays. But now, thanks to ALMA, we are studying the torus and in general all the circumnuclear material of nearby AGN in the sub-millimeter, and this has represented a revolution because it doesn't not only allow us to resolve the torus when we look at the coldest gas and also the molecular gas, but also to study the kinematics. And this is something that it's really providing a wealth of information, and allows us to study these connections, like I said, between the host galaxy and the supermassive black hole. So the other point I wanted to make is the importance of multi-wavelength studies in order to study AGN feedback and the torus in particular. So as we do with the astronomical objects, like for example, this is the Centaurus A galaxy, we put together data from different wavelengths in order to understand what's going on. And so here, for example, we have a view of the jet, of the dust, of the X-ray heated gas, sorry. And in the same way, we are collecting like all this observational data to try to understand how this torus structure works and develops. So this cartoonish view of the torus and surrounding material comes from this review from 2017, where we show the different structures, not the supermassive black hole surrounded by the accretion disk, the corona, the broadline region clouds, and the torus clouds. And in the polar direction, we also see some dust that, as we will see, it might be more or less important depending on the properties of the AGN. But this more recent scheme of the torus has been put forward by Sebastian Hönig in his 2019 paper. And this one, I like it because you can see, so this comes from putting together the information that comes from the different wavelengths. And I'm gonna use some recent results to try to explain what we are seeing here. So in the near infrared, we observe a very hot dust. So we are observing the inner parts of the obscuring structure of the torus. And for example, this is what we can see with instruments like gravity. This is a model image obtained from the gravity data published in Vermont and Collaborators 2021. This is the model that better reproduced the visibility that they have for NGC 1068. And what we see is an elongated ring, which inner radius is only 0.2 parsecs. So we are talking about something that is really, really small. So, and we like I said, we would be seeing this would correspond to the innermost part of the torus. I think Taro also gave Taro Shimizu did one seminar also explaining some of the gravity results, and This is another one that came up even more recently, I think. Then in the mid-infrared, we will also we also observe dust in the equatorial plane, what we understand as the torus, but also we observe in the case of some galaxies, at least, this polar emission that is shown here as a hollow cone. It has to be hollow because otherwise you wouldn't have you wouldn't get to see the broadline region from certain orientations, and we will kill all the type 1, type 2 AGN thing. In fact, and to explain when we observe this, let me introduce this GATOS collaboration, which stands for Galactic Activity, Torus and Outflow Survey. GATOS is a volume-limited sample of 12 Cipher galaxies selected from the sweep path catalogs that are very nearby AGN, Cipher-like luminosities. And when we observe them in the mid-infrared, which is shown here in blue in these images, we find that most of the mid-infrared emission observed from the ground, so with good angular resolution, is still unresolved. So when we are talking about the inner 150 parsecs, more than 60% of the emission is unresolved. It's still unresolved at this high angular resolution. But in 7 out of the 12 GATOS galaxies, we detect also a extended polar emission, no? Which is, like I said, this one that you see here in blue, and it's aligned. It coincides with the direction of the ionization cones observed in oxygen 3, which are indicated here with the orange dashed lines. And like I said, we observed this for 7 of the 12 GATOS galaxies. And then finally, this part of the diagram would correspond to what we observe, for example, in molecular gas with ALMA. And we found that the molecular gas is distributed in the equatorial plane. So again, back to the torus geometry, but on larger scales. So observing in CO and also in cold gas, looking at the far infrared continuum, we measure large tori with diameters that go from 20 to 100 parsecs in these GATOS galaxies, and are perpendicular to the ionization cones. So they are like big tori, let's say. No? And they are in CO are the structures that are shown here in red. Okay. So this is more or less how we get to this scheme that Sebastian put together, no? Like joining all the information that we have from the different waves. But now we are in position of trying to go one step further and not only say when we observe polar dust and when we do not observe polar dust, but trying to investigate what is producing this polar emission. Because it might be only dust in the narrow line region that is hit by the AGN radiation, but it might be also outflowing dust. So dust that is being lifted up by infrared radiation pressure. So in this diagram that is taken from the paper by Almudena Alonso Herrero and the GATOS collaboration, this is what we call paper 2 in our collaboration. Here we show the column density measured from the ALMA data for the GATOS galaxies versus the Eddington ratio measured from the X-rays. And the colors correspond to different X-ray luminosities as a proxy for the AGN luminosity. So more red objects correspond to the more luminous AGN in the sample. And also the different symbols indicate when we detect polar emission, when we detect some equatorial emission, all in the mid-infrared. I'm talking about mid-infrared now only. And when we do not resolve any structure, okay? And now in the diagram, we also show the prediction from a semi-analytic model. And this is the region of the diagram in which we would expect to see polar emission associated with infrared polar outflows. So these are the conditions that would be required to be able to see this infrared polar outflows. So it's a compromise between having a relatively high column density, not too low and not too high, because too high would be impossible to lift the material, no? And too low, you don't have enough for launching an outflow. And also you need a minimum Eddington ratio in order to produce these outflows. This is the range that have been explored by the models, only this short range here. So they should be expanded to a wider range. But what we found based on this prediction is that some of the targets for which we detect polar emission are in this part of the diagram in which we would expect the polar component to be associated or would be associated with the infrared polar outflows. And something that we see from this diagram also is that all the gatos in which we detect the polar emission have higher volumetric luminosity. They have the highest volumetric luminosity in the sample. In the case of the lowest luminosity AGN, we do not resolve any polar emission, which could be due to the fact that it's impossible to produce these polar dust outflows, or also that the sensitivity of our ground-based observation is not enough to see the polar emission if it's too faint. And for this low luminosity AGN, the JWST, for example, will be very important to disentangle whether there is this polar emission or not. A similar result was found by Omaira Gonzalez-Martin using a completely different approach. So here she did LCD fitting, infrared LCD fitting of a large sample of AGN, like tens of AGN in the nearby universe, using all the torus models that are available in the literature. And she found that also that the highest the highest volumetric luminosity AGN need the torus plus wind models to reproduce the SEDs, whereas the lower luminosity AGN can be even better reproduced with torus models without the wind component. So this could be taken as a further indication that as the more luminous the AGN, the more likely you are to see this polar component that might be associated with the outflowing dust. Like I said before, ALMA has been a revolution in the study of the torus because it allowed us to resolve the torus, not to obtain images of the torus in the some-millimeter range. And we have seen that the properties, for example, vary depending on the transition we look at. The size varies, the shape varies as well. NGC 1068 has been very well characterized by different authors looking at different transitions with very different resolutions. And also lower volumetric luminosity AGN have been studied by François Combs and collaborators. And they also have found evidence for large tori in CO and in coal dust. And like I said, for me, perhaps the most important thing is that for the first time we are starting to study the kinematics of these structures of the torus to understand how they are influenced or they participate in this gas flow cycle, no, that the AGN produces. So in this plot here. This is a very simple modeling done by Santiago Garcia Burillo in his 2019 paper, in which we estimated the mass in the torus of NGC 1068, the molecular gas mass, which is 3 times 10 to the 5 solar masses. And we found that half of the torus mass, a bit more than half of the torus mass, is rotating in the equatorial plane and practically unperturbed by the AGN feedbacks, by the wind and the jet and everything that's going on in NGC 1068. So if things continue like that, the torus can continue fueling the AGN for 1 to 4 mega years, approximately, which more or less coincide with the expected AGN lifetime of this AGN luminosity. And the other half of the mass in the torus, it's I'm going to say it's outflowing. We interpret it as an outflow, but what we can say to be fair is that there are non-circular motions. So half of the mass are streaming motions. that some authors interpreted as counter-rotation within the torus, like for example in Pellizzeri, Imanishi and collaborators, they interpret that the innermost part of the torus is counter-rotating with respect to the outer part. But in the case of this analysis done by Santiago Garcia Burillo, he interpreted the non-circular motions as a very 3D outflow, which has an almost polar component, but also an almost equatorial component that would be peeling out the outer layers of the torus. And the more polar component, it's lifting material in the outwards and actually connecting the torus with the circumnuclear disk of the galaxy, which is this one that we see here. The CND, the circumnuclear disk, is the molecular gas reservoirs of the AGN on larger scales. We are talking about a diameter of 200 parsecs now. And in the case of NGC 1068, we can see that it has this ring shape. It doesn't look like a disk, it's more like a ring. And actually, based on all the evidence that we present in this paper, this is actually an effect of AGN feedback, because the combined action of the AGN-driven wind and the jet, which is very important in NGC 1068, are pushing the molecular gas outwards and producing this ring-like shape. And like I said, the torus is connected to the CND through molecular gas streamers, which correspond to outflowing gas. This is our interpretation of the kinematics. And actually, the effect that we see so this morphology that we see in NGC 1068 is what it explains, or may explain these correlations that we see here for the Gatos and also the NUGA galaxy. We put them together to compare them. So the NUGA sample are AGN of lower volumetric luminosity than the Gatos galaxy. And here what we are showing is this parameter gives an idea of the concentration of the molecular gas within this inner 200 parsecs. Okay, so it tells you, galaxies sitting here show a higher concentration of the molecular gas in the inner 50 parsecs relative to the 200 central 200 parsecs. Okay, so we believe that what is happening is this, that because of the effect of AGN feedback, the molecular gas is being pushed outwards. And in the more luminous AGN with higher Eddington ratio, we have this kind of morphology, and we have most of the molecular gases in the CND. And in the case of the NUGA galaxies, which have lower volumetric luminosity, lower Eddington ratio, the gas is more concentrated on the torus scales. Okay, so this is this would be a manifestation of AGN feedback, affecting the innermost 200 parsecs of AGN. And this is summarized in this scheme that I show here. This would be the CNG, and this is what it would happen as we go to a higher AGN volumetric luminosity and Eddington ratios. For how long have I been talking so far? Half an hour?
Less, because we started late. So yeah, keep going. Okay. Yeah, you've been talking for about 23 minutes.
Okay, that's fine. All right. So now, this was a nice break, because so this is what I had to say about the innermost regions of this nearby AGN. So we start to see to understand the effect of AGN feedback on the molecular gas on these nuclear scales. But we can try to study this on somehow larger scales in higher volumetric luminosity AGN, also in the local universe. And in this case, we are targeting a sample of type 2 quasars, quasar 2s, that we have also observed with ALMA at a very good angular resolution. So this is, I'm going to talk about ALMA observations of a subset of the whole quasar feed sample that we also have observed in CO221 with the 0.2 arcsecond resolution. This is very good angular resolution, and this redshift is 370 parsecs on average. And this subsample of quasars that I have observed, comes from the whole sample, which has 48 quasars taken from the Reyes catalog of quasar-2s. So basically, we took all the most luminous and most nearby quasars in the catalog, which are these 48 quasars, and we targeted these 7 that I'm showing here with ALMA. The morphologies of these 7 quasars are representative of the whole sample, and they include interacting galaxies, mergers, post-mergers, spirals, and 2 red ETGs. They are more like elliptical-like. And this is part of a large program that we are trying to observe the whole sample with different facilities in different telescopes around the world. So mainly, of course, from the GTC in the Canary Islands, and we are obtaining near infrared observations for the whole sample, and also some IFU observations in the optical. We also have near infrared IFU data for the targets that we have observed with ALMA. Deep optical imaging of the whole sample to get to know the optical morphologies in detail, and we will propose for the James Webb to observe this pilot sample that we observed with ALMA. So like I said, so we went and observed these 7 quasar-2s, which have the same properties in terms of AGN properties. Let's say they have this more or less the same volumetric luminosity, which are around 10 to the 46 ergs per second, and the stellar masses of the host galaxy are also similar, 10 to the 11 solar masses, so massive galaxies with different morphologies. And when we went to and observed with ALMA in CO221, we detected all the interacting and the spiral galaxies, but we did not detect in CO the red ETGs, the elliptical-like galaxy. Something perhaps that could be expected, no? When we plot the masses that we measure from these CO221 observations as compared to samples like Atlas DD, which are red early-type galaxies, and also the cold gas sample, which includes spirals and also ETGs. So one first result that we got from these observations is that quasars with the same AGN properties practically and living in massive galaxy can have gas masses differing in more than 1 order of magnitude. No? So we have very gas-rich quasars in which there is a lot of star formation, very strong and fast ionized outflows. And we have, on the other hand, quasar-2s with very small molecular gas reservoirs forming much less stars, and in which the ionized outflows are also slower. So this is important when selecting your AGN samples, comparing to control samples. So morphology is something that we always have to take into account. And the radio emission might be also important, because this is also some difference that we found between our interacting and spiral quasars and the red ETGs, because these guys here have higher radioluminosities than the red ETG. So this is something that it might play a role as well. But let's focus on the quasars for which we have CO221 detections. On the top are the interacting systems, and at the bottom the spiral galaxies. So you can see the morphology are very different. So in colors we are seeing the CO221, and in pink contours the 1.3 millimeter continuum emission. And you can see that in the case of the spirals, well, this is what we usually observe in CO in spiral galaxy. The CO follows the spiral arms and the bars that these spirals may have in the optical. And in the case of the interacting galaxy and post-merger systems, the morphologies are more complex. The kinematics also are messier, as I will show. And actually, something that we find is that in the case, at least in the case of these two quasars, we also find evidence for this redistribution, or well, it may be a different causes, but something is AGN feedback is modifying the distribution of the molecular gas as traced by CO221 in these quasars. And here we are talking about 1-2 kiloparsec scales. Okay, so we find these double peak structures that you can see here that do not have optical counterpart. When you check HST observations or Muse observations of these quasars, you don't see the double peaks. You don't see this morphology. It's nothing to do with that. So we believe that these morphologies are probably due to also to the effect of AGN feedback. No, probably the combination of the jet and the AGN driven wind, and also how the ionized outflow coupled with the CO disk, as I will show. In the case of this galaxy, which is J1010, it's not so clear because so we see the double peaks. But we do not resolve a jet in the case of this galaxy, no, because the 1.3 millimeter continuum morphology is very rounded. Also in VLA observation at higher frequency, it's the same, so we do not see anything that looks like a jet. And also the ionized outflow has not been well resolved, and we don't have as much information as we have in this other quasar, which is the Teacup galaxy, a very famous object in which there is a jet, there is an outflow studied in different phases, and we have a lot more information. So in this case, we are pretty sure that the AGN feedback is produced in this peculiar morphology. And like I said, we studied the kinematics thanks to these ALMA observations, and here I'm showing this is the moment zero map, so the flux map, the velocity, and the dispersion maps of this Teacup galaxy, and this is the direction of the jet as traced by our 1.3 millimeter continuum. But the same orientation has been found from VLA data at a higher frequency. So the jet is more or less in the direction of the minor axis of the CO disk. And then, so what we believe is happening is that the jet somehow is pushing, no, the combined action of the jet and the wind. They are pushing the molecular gas outwards and producing this morphology. And actually, there are more examples of these on kiloparsec scales, like for example, in the Cipher2 galaxy NGC 2110, studied by David Rosario, in which they also observed this region devoid of CO221 in this galaxy, in the central kiloparsec of the galaxy, and they did all the comparison with the optical morphology, the also warm molecular gas observing the near infrared, and color maps, etc. And they interpret these observations, so this depletion of CO221 as the effect of AGN feedback. In this case, what they propose is that the gas is excited to higher transitions, so we might be able to see CO in like I don't know, CO 6 to 5 or even higher than that, but not in CO 2 to 1. But it could be also the effect of the outflows or the jets, no, that are pushing the molecular gas outwards, as we saw in the case of the nearby Ciphers, but on smaller scales. And then to interpret the kinematics, which is very complex in the case of these quasars, we did modeling with Barolo. So we've tried to fit a very simple model to describe the galaxy rotation and interpret the non-circular motions. So this is the data, the model, and the residuals for the velocity and the dispersion maps. So for example, studying the residuals along the minor axis, when we subtracted the rotation, we can see if there are remaining blue shifted or red shifted gas, as this is the case. And considering the morphology of the galaxy, the orientation, which is the far side, the near side, etc., we work out where is the region of the galaxy in which the non-circular motion correspond to outflowing or inflowing gas. And to help us with that, we use these position velocity diagrams. I don't know if you're familiar with them. I wasn't, but I am now. So this is the position velocity diagram along the major axis of the galaxy, which would be this one of the CO disk, sorry, which is good to characterize rotation. So the red contours are correspond to the model that we are using, and the yellow dots are the average velocities of the model. And then the position velocity diagram along the minor axis is the one we should look at in order to interpret the non-circular motions. Because are the ones with non-null projections in the plane of the disk, assuming that the molecular outflows are always mostly coplanar with the CO disk. We are always working under the assumption that the AGN-driven molecular outflows are coplanar with the CO disk. Okay, this is the assumption we work with in order to interpret this kinematic. So, for example, in the case of the TCAP, we found that there are non-circular motions, beyond the Barolo contours, which correspond to outflowing gas in these parts of the diagram. And the molecular gas in this case has reached velocity of up to 250 kilometers per second. So not very fast, but this is what we normally expect for molecular outflows, not as fast as what we measure in the ionized outflows. In the case of the interacting galaxies, like this one, like the TCAP, everything is messier because there are mergers for merger systems, so the kinematics are very perturbed, and actually it's even difficult to fit the galaxy rotation because sometimes it's not a perfectly rotating thing. But in the case of the spirals, it's more straightforward because there are disks, they rotate, and you can reproduce better the gas with the rotating this model. And then in the position velocity diagram, you see what you would expect from an outflow developing in the plane. This positive negative pattern, that corresponds to gas that it's outflowing, and it's becoming decelerated as we move from the center of the galaxy. Okay. And in the case of this galaxy, J1100, we see that the non-circular motions are mostly blue shifted. There is some red shifted gas, but most of the flow of the gas is blue shifted. And this is something that we can also see from this continuous subtracted, model subtracted velocity map, where you see the blue shifted gas here that corresponds to the outflow and a bit of red shifted gas. Because in the sub-millimeter, we see both the red shifted and blue shifted part of the outflow. So to finish with, trying to summarize a bit here, we measured the properties of the outflows. So for one of the quasars, we couldn't resolve it, so we didn't measure the mass. But for the other four, we get estimates of the mass that we found in these outflows. And we found that in the case of these parallel galaxies, we found the more massive outflows. And actually, in this spiral galaxy is where we have evidence that the ionized outflows are in the plane of the disk, so they are coplanar with the CO disk and with the galaxy disk in this case. And in the other two, the interacting systems, which are more messy, more complicated, the ionized outflows would subtend a larger angle relative to the CO disk. And actually the masses that we measure for the molecular outflow are smaller than in the spiral galaxy. So it can be something related to the coupling between the jets and the ionized outflows and the mass than you are able to drag in the molecular outflow. And the outflow mass rates that we measure are all around 10 solar masses per year. which are very modest for the AGN volumetric luminosity that we are talking about. In fact, if I plot the outflow rates of the quasars in this very well-known plot by Fiore, here in blue, no, it's the expected relation that that they found for the molecular outflows. We see that at this volumetric luminosity, we would be expecting outflows of between 500 and 1,000 solar masses per year, something that we only observe in ULIRCs. And in this quasar, we are measuring 10, well, this has the 3 factor, no? You have to multiply by 3 because of the outflow geometry that they are using, so it would be 30. So they are very mild molecular outflows. Although I have to say that the way in which we are measuring the molecular masses of this outflow, it's very conservative. So our masses are very, very conservative. But we are never going to reach 500, 1,000 solar masses per year, that for sure. So one conclusion from our study is that the outflow mass rate does not only depend on AGN volumetric luminosity and other factors like the jet power or the coupling between these jets or ionized outflow are key to drag molecular gas and produce more massive molecular outflow. No? So we would be talking about a scenario like this, no, of a strong coupling where we have everything developing in the plane of the disk, and then you are able to drag more molecular gas outwards. And in a case like this one, you barely touch the CO disk, and then it's very difficult to launch a coplanar molecular outflow, okay? So this is something that we need a much larger sample to be able to understand if this if the geometry, no, the different components is important, no, in order to have higher or lower outflow rates. So in summary, well, I think I can leave the summary here. I just wanted to emphasize that in order to understand not only the torus, but how AGN feedback works from the central parsecs to up to kiloparsec scale, we need multi-scale and multi-phase observations. We found evidence for AGN feedback shaping the nuclear and circumnuclear environment of nearby AGN of different luminosities, as I have shown. And like I said, the outflow mass and the outflow mass rate do not depend only on the volumetric luminosity, but other factors need to be taken into account. And I stop here. Thank you very much. I think I went for too long.
No, thank you very much. That was really great. It was very exciting. I'm sure there's going to be a lot of, yeah, there's already a bunch of hands. So Giacomo?
Hi, Cristina.
No.
Hello. Really nice results, amazing results. I was especially surprised about the TCAP, the results on the TCAP that you showed with the molecular gas. And so it's surprising, but at some point, yeah, it fits with the picture in which the molecular gas is depleted in the direction of the jet and the outflow, right? So what really surprised me is that direction of the kinematics. So basically, this is a disk which is rotating fairly normally, and as you know, I am studying the ionized part, so the ionized gas, and this needs to be confirmed. But it seems that on very large scales, so on the scales of the giant nebula, the gas seems to be rotating. So in the direction of the jet and the AGN bubble, whatever, so perpendicular to the molecular gas. So possibly this could be an effect of the post-merger, so of the past merger. So the two remaining rotations of the merged galaxies. So one could be this molecular disk on smaller scales, and the other could be the remaining of the large scale disk, but the gas. But yeah, we will see. We will chat again about this. And so I wanted to ask you, I didn't quite understand what's your take on the outflow in the molecular phase, because you talked about coplanar outflow, so coplanar with the disk. I'm not sure I understood well.
Okay, yeah, so let me say about the TCAP. Yeah, we have to talk. This system is so complex, right? Because there is all the stuff going on the scales of 10, 15 kiloparsec, no? And then this that we are observing here, it's very compact, no? The molecular outflow, it's really compact. Everything is happening in the central half of kiloparsec or so, no? Central kiloparsec as much, no? So quite compact. As you might expect for molecular gas, actually, right? And then the coplanar thing, so this is something that we need to assume in order to interpret the kinematics, because so based on observational evidence, no, the general idea is that in the case of starburst-driven molecular outflows, these are generally perpendicular to the CO disk, like M82, for example. But then, in the case of AGN, so the evidence that we have for the targets that have been observed is that the molecular outflows normally happen in the plane of the disk. So it's very difficult to lift molecular gas in the sort of perpendicular direction, right? If you know what I mean. So if, when you have like a jet or something that is dragging the molecular gas outwards, what you see, so the molecular gas, okay, it's not completely in the plane. It will have a 3D geometry, but it's very directional in the plane of the CO. And so based on this observational evidence, this is something that we assume in order to interpret the kinematics, because then when you can look at the PV along the minor axis, to interpret what it's outflowing, what it's inflowing, etc.
Okay, thank you. I got it. I might have another question, but I will wait for later.
Okay.
Other ones will have asked.
Okay, I think Subhashish was next.
Hi, Cristina. Wonderful talk, wonderful results. Just two short questions. The first one is, what geometry do you assume for calculating the mass outflow rates? Because the distance is kind of like very sparse, like from a few hundreds of parsec scales to a few tens of kiloparsecs, and then you have different cones and different planar and coplanar geometries. So what is the distance scales and the geometry that do you assume for mass outflow rates? And the second question is, correlation with the AGN, current AGN activity state and the molecular outflow rate, because is a bit of a question, because there is a light travel time, or even there is interaction time, because it's a long way, like 1 kiloparsec, it takes time to travel. So how do you relate the current AGN state with these mass outflow rates and stuff? Because something may have happened. You have shown in the first few slides that AGN flickering timescales can be very short. And so that's the question that I want to ask you. So I mean, these two questions. Thank you.
Let's see if I remember everything. So the radii that we are measuring for the molecular outflows are these. So between 0.5 and 1 kiloparsec for the ones that where we have good measurements. So this is more or less this slightly larger than the radii that are measured for Seyfert Galaxy, and more or less the same that they are measured for ULIX. We might be missing some more diffuse molecular gas that we might trace with other transition, but based on our CO221 observations, this is the radii that we measure, no? And I have compared with other works using the same CO transition. Then for the geometry, we are not using the 3-factor inferior. So we are assuming the sphere geometry, no? And it's only velocity, how is it? Mass, velocity, and rate, right? What else?
Yeah, because the geometry and the distance factors can actually be quite large, because in X-rays, for example, I have worked on X-ray outflows. The distance is a very, very big quantity. I mean, we have large uncertainties on the distance scales, and it can be orders of magnitude. So I was just inquisitive, like how accurate, I mean, if you put an error bar on the mass outflow, it's how large will it be? So that was my question.
So here for the outflow radii, we have very good determination because the resolution of ALMA is very good. It's like I said, 300 parsecs. No, so we resolve them, and we can measure them well from these PV diagrams, for example.
Okay.
And then yeah, depends on the geometry that you assume. You get one outflow rate or the other. Like for example, I use the factor 3 because I wanted to compare with the Fiore plot.
Okay.
But in the table, I'm not considering the factor 3. And then for the time scales, right? So let me see. So I think you mean if these molecular outflows can be related to the current AGN episode. And I think the answer is yes, because they are very compact. And for example, I don't remember, I'm very bad at calculating things in real time. But as far as I remember, in the case of ionized outflow, for example, for an outflow of 1,000 kilometers per second in velocity, it takes like 1 mega year to reach 1 kiloparsec or something like that. It was like a simple thing. 1 mega year to reach 1 megaparsec. So yeah, in principle, I mean, we are talking about the dynamical timescales, no, of this AGN that we have. So I think, yeah, it could be launched by the current AGN episode. That was the question.
Okay, thank you.
Conrad?
Hi,
Yeah,
Conrad.
thank you for this very nice talk, very nice, and also for the additional explanation on the outflows in the plane of the disk, because that was also something I was a bit wondering about, and I actually have to think a bit more about why you mainly see it in the plane of the disk and not also in the polar direction. But my actual question was on the two sources where you actually did not detect any molecular gas, if that I understood that correctly, because sometimes my connection was also not so good. And so I'm actually wondering, what is your take on this? Why did you not? Because these are type 2s from what I understood, right? So there must be some obscuring material somewhere. So why is it just a matter of sensitivity? We have to go deeper to see the molecular material, and what one could be going a bit further on that. What can we say about molecular material being the same as what we see as the dusty material? So could it be that we are actually having the two are not really tracing the same material, or yeah, I don't know. Yeah. So what's your take on this?
Okay, so let me think. So I think it's a matter of sensitivity. I think for the so here we are talking about total molecular masses, no? So the whole of the galaxy. It can be in the nuclear region. It can be very different. I'm sure that if you look, if we will be able to have the same resolution that we have for NGC 1068, we will be obscuring material in the parsec scales, no? But in the galaxy scales, I didn't say, but so this is like 10 to the 9, 10 to the 10 solar masses, no? In the quasars with the CO detection. And for the others, we estimate 3 sigma upper limits of less than 10 to the 9, no? A bit less than that. So yeah, I think the main thing is the difference, right? So the difference between this quasar here and these ones here, it's huge. That doesn't mean that those do not have any molecular gas. I mean, they will for sure, but it's much less than in the other quasars. Mm-hmm. So I think what I'm proposing in this paper that I'm hoping to submit before the end of the month is that so in these quasars so everything is happening at the same time. No, there is a star formation, there is outflows, molecular ionized outflows. The depletion times are more or less the same as we found for non-active galaxies. Like AGN feedback is happening, and there is plenty of cold molecular gas. In these other ones, we might be witnessing a more evolved stage of the AGN, no, in which the molecular gas reservoirs have been are more depleted by the action of the feedback, and because of that, we find lower masses. Also, like I said, the ionized outflow properties are different. No, the outflows are more compact and slower than in the other ones, and also the radio properties were a bit different. So they might be different types of objects, or they might correspond to different stages in the evolution of AGN. No? And what else did you say? Yeah, but in the nuclear region, we don't know what's going on because, like I said, we are just resolving the inner 300 parsecs. And I don't know if I'm missing.
Okay, no, thanks.
And yeah, and the thing.
I don't know.
What you say about the molecular outflows developing in the plane of the disk. So my take is, that it's very difficult to lift up the molecular gas. Yeah, you were saying about the correspondence between dust and molecular gas, right? So for example, in the spiral galaxies, normally there is good correspondence between the dusty features that we observe on galaxy scales and the cold molecular gas. In the mergers, everything is more complicated. But in general, usually there is good correspondence between dust and molecular gas, yes.
Okay, thanks.
Okay, Giacomo, did you want to ask your second question?
Yes, thank you. No, my other question was on the first part of your talk, so on the study with Gatos. So if you found some differences between galaxies having a jet or without the jet, or if all of them have a jet. I don't know actually about all of them. I don't know if you found some differences and how this fits in your scenario in which when you go at higher luminosities, you start emptying the region around the nucleus. So if you can simply do it either with the wind or with the jet, creating a cocoon, expanding like in the Morganti works, just to cite one.
Yeah, good point. Actually, I didn't say that, but so these Gatos that I'm showing here, no, which are the ones that are supposed to be more like this, no, like having more molecular gas in the outside part in the CND, are the ones with detected molecular outflows. So the others. I think there is no detection, no, or we cannot resolve them or whatever. But these 5 for sure, they have molecular outflows detected. And NGC 1068 for sure, no, there is the jet and the jet in combination with the wind are producing this morphology. For the others, I'm not sure. I mean, there is not a jet like in NGC 1068 as powerful, but probably all of them to some degree have some sort of compact jet or something like that, no? That may be helping, no, to do that, because in the case of NGC 1068 it's clear. And but yeah, at least what we see is that these have molecular outflows. And trying to fit this, no, with the last part of the talk, no, if you need the action of the combined action of the wind and the jet to drive the molecular outflows, it might be related to that, yes. And actually, going back also to this, to the Fiore plot, no, something that I checked when I was comparing the measurements for my quasars with other measurements, no, for AGNs of different luminosity. Something that you realize is when you look at Seyfert's like NGC 1068 and Rafaela's like IC 5063, you find much larger mass outflow rates, no, in molecular gas than for the Seyferts, the normal Seyferts, let's say. So I think having a jet in the right direction, because also in Rafaela's object, no, we know that the jet it's in the plane of the disk. It helps us to boost the mass and the outflow rate. So I think this is what is happening, and I like to see more of these quasars, because maybe we were not lucky, and we look at the ones that didn't have powerful jets or winds or whatever, not to launch more massive molecular outflows.
Yeah, because that's weird as well, right? Because they are also jetted quasars, and they are low power jets as the jets in the Seyferts that we are discussing, like 1068. It's a low power jet. So it's weird that they fall below. Maybe they are too low power even for being low power. Yeah, could be.
Yeah, because maybe you need even higher power, because the molecular masses are higher, no? So
yeah, because you're rescaling everything as everything is bigger. Yeah,
you have more mass, no, more molecular gas mass, and
Yeah.
if rotating, it must be more difficult not to push this molecular gas than in the Seyferts, I guess. No?
Could be.
So if any of you in the ALMA attack in the next cycle, and you see a proposal about quasar 2s, please give us.
There is no ARM attack anymore, right? They have distributed.
Yeah, true. That's true. Yeah.
No, there's Almatac for large programs, right?
Actually, it was like that. I don't know how it will be in the next ones.
Great. Shavita?
Hi, Cristina. That was an amazing talk and amazing data. Actually, my question was the same as Giacomo's, but I will ask a different one now. I was just wondering, eventually this, AGN feedback is supposed to quench star formation, right? And I just wanted to see, are there any, have you looked at the stellar population, or are there any star formation rate maps and how they relate to the maps of the outflows?
Okay, yeah. So something that I didn't mention also is that, for example, so these outflows that we are measuring here for these quasars, like I said, they are very mild. So I measured the depletion times that we expect for these outflows. So this is the molecular gas mass divided by the outflow rate. And it's like around 1 gig a year, a bit less in this case. But so in comparison with the depletion times that we get from the star formation rates, so these are less efficient, let's say, in depleting the gas. No, so the galaxies are more efficiently depleting the molecular gas by star formation than because of these outflows. So nothing to do. So the most powerful molecular outflows that we are finding is in Julius. There is like a huge difference, no, between what we see in the Seyferts, in the quasars, and what we see in the Julius. But so they will be having some effect in the host galaxy in quenching star formation. They do have some effect, of course, but like I said, even less than what is associated to star formation. At least in terms of gas ejection. Something that I always say is that we are always putting all the eggs now on the basket of ejecting the gas only, and this is the only thing that we looked at. But the effect of AGN feedback can be more gentle and can happen in different ways. I mean, in terms of ejecting gas from the galaxy, we know that it's super difficult, no? And even if you are able to drag gas outwards, it drains back at some point, most of it. But maybe simply by perturbing the gas, it might be enough to keep at least the region of the bulge quenched, no, or under control, let's say. So I think yeah, probably the effect of AGN feedback, at least in these not so extreme objects, it's more gentle than what we were expecting. At least for sure, we know that it's having some effect on the distribution of the molecular gas in the central parsecs and up to 1-2 kiloparsec scales. And in cases like the teacup, for example, like Giacomo was saying, no, I'm talking about the central 1-2 kiloparsec, but these galaxies, for example, have huge bubbles, no, that so there is, you see that the effect of feedback goes beyond that, although it could be related to a previous episode.
Thank you.
So I have a very general question. You mentioned several times in regarding your objects, the ones that you observed, you mentioned comparisons to ionized outflows. Some cases you said there was no there were no observations. In some cases you said they agreed. So just from everything you've observed, what's your general summary of how the two relate, the molecular outflows to the ionized outflows, in terms of scales and velocities and power and anything else you want to elaborate on?
Yeah, for example, so in general, I think they are independent in the sense that sometimes we see ionized outflows that have a completely different orientation to the molecular outflows. And in some cases, they are both coplanar, no? Like, for example, in this galaxy that also Giacomo was mentioning, IC 5063, that have been modeled, have been observing all the wavelengths that you can imagine. And both the ionized outflow and the molecular outflow are taking place in the plane of the galaxy. So what we believe, so in general, the ionized outflows are much faster than the molecular ones. So molecular, we are talking about 100 kilometers per second, 300 kilometers per second, things like that. And the ionized outflow, 1,000 kilometers per second or even more. But in terms of mass, also the ionized outflows are normally a bit more extended than the molecular outflows, but still the bulk of the mass that you are dragging outwards, it's in the molecular phase, no? And there are, for example, the papers by Fluech, no, in which they compare the molecular and ionized and neutral outflows in AGN, and the molecular phase is the one that carries the bulk of the mass. In AGN-driven outflows, and then the relation between them. So what we think is that maybe the ionized outflows are also contributing to push this molecular gas outwards, no? Depending on how they are relative to the galaxy. Like, for example, if it's something like this, it's gonna relate very little to what is happening to the molecular gas. But if it's developing in the plane, then it may be helping, no, to contributing to drag the molecular gas outwards. So in principle, I would say generally they are decoupled. I mean, when they coincide, it's because, well, I don't know, it might be because of the condition of the material, no, that the wind encounters as it develops. But in principle, we don't find the same orientation for the two of them. Always talking about the way in which we are interpreting our kinematics, no, which is quite complex.
Great, thank you so much. Any other questions? Vivian left you a message on the chat. Any other questions or ways in which you want to collaborate with Cristina? All right, well, let's thank Cristina again for a fantastic talk.
Thank you so much for inviting me. It has been a pleasure to talk to you all.
Great,
Thank you, bye-bye.
Bye-bye. Thank you.